This afternoon, I wanted to present some information about transformers, and in particular, about transformer turns ratio testing. But before we got too far into that, I wanted to just use this introductory slide to show you some variations of transformers. Now, what you don't see is control type transformers that are used in all kinds of electrical equipment and everything. But what we want to talk about this afternoon are those transformers that are used in electrical transmission and distribution of electrical power. And you may see some here that look like something that you'd see in a URD circuit or something that's in the corner of your yard. There are others that you see that you might have seen at times sitting on poles. And then there are others that you may or may not have seen or paid attention to that actually would sit in a switch yard or a substation yard. Anyway, there's a variety of transformers. Even in some of these larger transformers, you'll see that it's really apparent where the main tank of the transformer is, and others that have so many radiators and fans on them, you wonder, where's the transformer? So just to let you know, there's quite a variety, and we'll talk about transformers in general and how we might perform a transformer turns ratio test. Going on to the first slide here, we want to point out that there's a standard that guides a lot of our testing, and IEEE Std.C57.152 is one that it spells out the recommended diagnostic field test on fluid-filled, liquid-filled power transformers. When you get into some of these larger transformers, they actually are insulated with oil and with cellulose products for solid insulation and everything, a combination of those two things. But some of the tests that are spelled out in this standard is power factor testing. Some would refer to it as tan delta testing, and they're very, very similar. Dissolved gas and oil analysis is very important. It can tell us a lot about what's actually going on internal to our transformer without actually having to open it up. Additionally, we can do insulation resistance tests. It's a DC insulation test as opposed to power factor, which is an AC insulation test. There's core ground test, which is a variation of the insulation resistance test. I'm going to skip over the transformer turns ratio here for a moment and go on to excitation. Excitation current is a test that we would normally perform whenever we were doing power factor testing. And then frequency response analysis is another type of testing recommended by this standard. And then finally, we want to talk more specifically in our presentation this afternoon about the transformer turns ratio, or a lot of people would just simply abbreviate that to a TTR test. Going on to the next slide, we want to point out that there's an awful lot of information that can be found on the nameplate of a transformer. So before we actually perform any kind of test on a transformer, we'd probably want to gather all the information we could from the nameplate. Three specific items that we need to know before doing transformer turns ratio test is the primary voltage, the secondary voltage, and the relationship between the primary and the secondary. So the primary voltage is the voltage being applied to the transformer, and then you could think of the secondary voltage as the output of the transformer. And the transformer vector group is just simply the configuration of the windings and how they relate to one another. And then there's quite a bit more information that you can gather from the nameplate of a transformer, but we're not going to talk about those specifically at this time. We're going to talk about more so those things that we know that we need for a transformer turns ratio test. On the next slide, we actually see an example of a kind of a simplified nameplate. And you see that, first of all, we know we're looking for primary voltage, secondary voltage, and the vector relationship between the primary and the secondary. So the very first thing that we see off to the left here is that it's a 480 volt primary, and because the primary is a delta, it shows a line to line or phase to phase voltage. You'll see that this diagram is a delta, that the terminals are labeled with H, so we know that it's associated with the primary winding. And then you see the 480 volts between the corners of the delta. Just think in terms of when we call something a delta, think in terms of a triangle, or if you're familiar with the Greek alphabet, you may think of it as a delta from the Greek alphabet. Then we can go look at the Y, or the secondary side of this transformer. We know that it's a Y because it's shaped like a Y. It has each of the phase windings connected at a common point. One end of each of the phase windings is connected at a common point, and we label that with an N as neutral. The nameplate tells us that this line-to-line or phase-to-phase voltage is 208 volts. If we look at the next piece of information, it tells us that the phase-to-neutral voltage, or the line-to-neutral voltage, is 120 volts. Now, if we didn't have both of those supplied to us, we'll see in just a little bit that we could have calculated one from the other and vice versa. We also want to say that because it's a delta in relation to a Y, there's going to be a 30-degree shift in the relationship between the two windings of the transformer. We'll see that in the next slide. So in this slide, we'll show the phase angle relationships, but we'll also explain what we might identify as an ANSI vector group. It's just simply some numbers and letters that are put together to designate or to identify the transformer configuration. So as we see, we start out in this DYN1. So the very first letter is a capital letter. And because it's a capital letter, we know that it's associated with the primary winding, with the high voltage side, the side of the transformer that we're applying voltage to. So we designate that as a delta in the triangle with the terminals that are labeled H1, H2, and H3, so we know that's the primary. And as you can guess, the very next letter, it's not a capital letter, it's a lowercase letter, and so we would probably want to associate that with the secondary or the output of the transformer. Again, it's identified by the fact that one end of each of the phase windings is tied to a neutral or a common point. And by the way, that Y could be turned right side up, upside down, pointing the other direction. However, it may be configured, but it's still a Y because one end of that phase winding is always tied to a common. We know because it's a Y that it has this neutral to the configuration, but we don't know that that neutral is brought to the outside of the transformer. So if you'll see also a lowercase n right after the lowercase y, the lowercase n says that we associate that with the secondary or the Y transformer winding. And what that says is that that neutral that exists in the Y has been brought to the outside of the transformer, and we actually have access to connect to it. And then finally, we've got a number on the end of this. This relates to the phase displacement between the primary and the secondary windings. And we'll illustrate that here just to understand it a little better. If we look at the H1 to H3 winding on the primary, we can bring that out and just set that out separate so that we can see the relationship to the secondary winding. So all of our references have to be back to the primary winding, and because the primary is a phase-to-phase voltage, that's what we want to compare to on the secondary side of the transformer. And so if we take that and overlay it in reference to the primary side, we see that there's a 30-degree shift between the two. That's what that 1 at the end of this ANSI vector group is indicating, that there's a 30-degree shift. So each number, 0 to 11, is representative of a multiple of 30 degrees. If we were to calculate, we were given in that nameplate a line-to-line and a line to neutral voltage for the secondary winding. But if we had one or the other, we could calculate the other. If you see the formula off to the left-hand side of the screen, a phase-to-phase voltage is equal to the phase to neutral voltage times the square root of 3. And if you were to punch that into your calculator and put in the square root of 3, then it would come up with a number that was approximately 1.732, and maybe however many digits your calculator would calculate that out to. But if we actually apply that, we had a line to neutral voltage of 120 volts, didn't we? So if we wanted to, we could have calculated that 120 volts times the square root of 3, or 1.732, is approximately equal to 208 volts. With that in mind, I want to just go to the next slide and show you just a very small portion of the ANSI, a list of the ANSI configurations, and you'll see that they're labeled in terms of their vector groups. The one that we've been looking at is on this third line, and it's designated DYN1. So it's a delta Y with a 30-degree shift. That 30-degree shift, that makes it to where in calculating ratios, we would take the high side voltage, divide it by the secondary side voltage, and then multiply that times the square root of 3 to get our ratio. And that's the ratio, our calculated ratio, that we'll compare to our test results. I just wanted to point out that the designation just above it on line number 2 is a DDO. That is, capital letter relates to the primary, which is a delta. The small lowercase letter relates to the secondary, which is a delta. So they're both delta. And the 0 out at the end of it says that there is no phase shift between the primary and the secondary. So this is one of the more simpler things that you can test, transformers that you can test and calculate the ratio. Because there is no phase shift, just take the primary winding, divide by the secondary winding, and that's your ratio. If you have any questions about what's shown on this, you can find this table pretty much in any of the test equipment manufacturers that supply transformer turns ratio test sets. And there's a path that's labeled at the bottom of the screen where the folks from Protec can go and they can look at what's been pulled out of one of the manufacturer's instruction manuals. It's several sheets. One manufacturer, I believe, if I'm not mistaken, actually has laminated cards that puts it in the sleeve of the cover of the test set. So they're readily available. You don't have to remember all of this stuff. Just have access to this table and you can pretty much figure out what the diagrams on your nameplate represent and how you might go about designating that in the test equipment if you need to in terms of a vector group, and then what kind of calculation you would make in order to compare to nameplate information or the actual test results. In the next slide, you see we put that ANSI designation up there, DYN1. We also put the diagram up there, but we wanted to show you a screen of one of the pieces of test equipment. You'll see that the primary and the secondary, the transformer, are separated by a colon. The very first one is a triangle, so that's a primary. Primary always coming first. We'll show a delta, and in the secondary, on the other side of the colon, you see a Y with a exposed neutral, and then the 1 indicates the 30-degree shift between the two. The next slide is just simply something I wanted to use in explaining a little bit about the way a transformer works. This is just a single phase representation of a lot of what folks may experience in the field. There is a primary and a secondary winding, and the primary winding has a specific number of turns or loops around the core, and then the secondary winding also has a specific number turns around the core. And the ratio of the primary turns in relationship to the secondary turns is approximately equal to the ratio of the primary voltage being applied to the secondary voltage output. Our transformer turns ratio comes not so much from an electrical circuit as it is an electrical to magnetic transformation. So when we apply a voltage on the primary side, there is an equivalent in the magnetic world to current that we would think of in an electrical world. So magnetic flux is channeled through and circulated through the core of the transformer based on what we're applying to the transformer, and as it passes through the secondary winding, it induces a voltage on the secondary winding. Going on to the next slide, you can kind of see a diagram of how a three-phase transformer might be represented as opposed to the one that we just looked at. You see the core is a little bit differently shaped in that it has three legs. This is what's referred to as a core form transformer. And you have three primary windings and you have three secondary windings, and I'm a little bit confused. There's only three legs. How do we do that? Well, if you look at the top view, and you'll see more of this in the next slide, but if you look at the top view, you'll see that there are actually two windings around each of the core legs. The inside winding is the low voltage winding, or the secondary winding. The outside winding is the high voltage or primary winding. So one is wound on top of the other. The secondary winding and the primary winding do not ever come in contact with one another, nor do they come in contact with the core. But their relationship is completely a magnetic one that's set up in the core of the transformer. Going on to the next slide, you kind of see that. You see the core. You see the three legs of the core. Looks like an 8 that's set on its side. And you see that there is a secondary winding wound on first on the leg, and then outside of that a primary winding is wound on that leg of the core. One other thing that I might just point out, just an interesting note, it's not key to our performing transformer turns ratio test, but notice what that core looks like. It doesn't look like one solid piece of metal, or at least it looks pretty rigid on the edges, and that's because it's not one solid piece of metal. It is a number of laminated conductors. In other words, insulated conductors. They're layers of magnetic steel that are stacked together to form a singular core. And the reason they do that, again, this is just ancillary information, is to reduce losses that might otherwise occur in a solid piece of conductor. Now we want to kind of look at the transformer that we'll be testing here in a little bit. We're going to apply some of the things that we've learned about transformer turns ratio testing. I know somebody will point out maybe that IEEE C57.152 is about liquid-filled transformers, and this transformer is not in liquid. It's a dry type transformer, and that's okay. For our purposes, it is just for our learning and our ability to get some experience in performing these tests. But you'll notice the marking on the transformer, the orientation of the nameplate. So these terminals in this transformer are very well marked. But if we didn't have those labels on the terminals, we could get an idea just simply by looking at the nameplate. So I've blown up a portion of the nameplate and expanded it and put it out to the side of the transformer in this slide so you can see the orientation of the nameplate is right side up from the perspective that we're looking at it, with the H terminals being on the top side and the X terminals being on the bottom side. And you'll notice on the nameplate, if it's oriented correctly, it also points out that your H terminals will be on the top side of the transformer, or your primary terminals, and your X terminals, or your secondary terminals, will be located on the secondary, or on the bottom side of the transformer. Also, you can notice that the nameplate kind of spells out the order in which those terminals are placed. In other words, from left to right, it would be X1, X2, and X3. And same thing for the high side of the transformer. Moving on to the next slide, we've got the actual nameplate of the transformer that we just looked at and that we're going to be going out and testing here in just a few moments. Again, it's one of the simpler types of configurations. It's a delta transformer. We can tell that by looking at the diagrams in the bottom, and that there is no phase displacement. So it's the DD0. We'll also notice that the primary and the secondary voltages are labeled, and I've put some additional labels on there so we can notice those. So it's 360 volts on the primary side and 247 volts on the secondary side. That's the nameplate voltages, and that's what we're going to calculate the ratio from. You'll also see that the common windings that we're going to be looking at, that the A phase winding for the primary will be H1 to H3, and X1 to X3 on the secondary winding. That's the comparison that we'll make. And the same thing for the other two phases. Finally, because we know that we have a very straightforward calculation here, we can just simply take the primary voltage, divide it by the secondary voltage, and we can calculate the ratio of this transformer. What's interesting is we're not done. We know, at least from our calculations, what the ratio should be, but we haven't tested it to see if it actually is, and that's the whole point of this. If we look at, in the next slide, what's an acceptable test result, you can see that IEEE C57.152, this is the one that we referenced earlier, a guide for diagnostic field testing and fluid filled power transformers. The tolerance of ratio, according to that standard, should be within 0.5% or 0.5% of the specified nameplate voltage of all of the windings. So if we look back, we calculated the nameplate ratio, 360 volts divided by 247 equals to 1.4574. So if we know that we have a tolerance of 0.5% or 0.5%, then we can also calculate the acceptable tolerances for the test results after we perform the test, right? So the lower tolerance is just going to be minus 0.5%, which makes it 1.4502. You see the calculations there. The upper tolerance is going to be 1.4574 times 1.005, or 0.5%, and that should equal to 1.4648. So there's our tolerances. If it's between 1.4502 and 1.4648, then we're all good. We've got the green light. We're good to go. If we fall outside of those, then we may have something else where we throw up a red flag and say, we need to understand why this is. And we can't put it back into service until we do, or can explain why it's not. Then if we go on to the next slide, it's our cue to just say, let's take these things that we've learned about transformer turns ratio testing and let's go apply them to this specific transformer. So let's make some practical application of what we've learned about transformer turns ratio testing. Let's start with some features of the test set. The first, and maybe one of the most important, is the equipment ground. As you can see here, it's an external connection to the test equipment, grounding the outer case of the equipment. We also have a ground that we get through the power cord to the instrument. It supplies a third prong, which is the ground connection to the instrument, and this allows us to have the safety feature as well as a reference for the instrument and the measurements that are being made. Additionally, we have an emergency stop button. If you just simply press that, if anything were to be wrong, then you can twist and release it. You'll notice the display shows that the emergency stop button was pressed, and it would interrupt the output. Additionally, we want to go to the connections for the high side and low side of the transformer, H being primary, X being secondary. Here's the H side. Simply center it over the keyed connector and then twist to lock it in place. So again, this is the X leads for the secondary of the transformer. We're going to center it over the keyed connector, turn it till it falls in place, and then twist the collar until it locks in place. Now we have that all situated. Notice also indicators that says the output's energized, as well as one that says you're safe to connect or disconnect at this time. Okay, so the connections of the test leads, you'll notice all of the high side leads have red insulated handles. This is the H1 lead, then the H2, we're connecting to the corresponding terminal of the transformer, and then the H3 lead as well. Now this is a delta, so there is no neutral. Here's the neutral lead, so just to keep it out of the way and everything, we're just going to go ahead and clamp it onto the insulation of one of the other terminals. So it has no connection, it's just out of the way. Now we're going to do the same thing on the secondary side of the transformer. You notice X1 was connected to the corresponding terminal. This is the X2 lead, and then the X3 lead being connected to the X3 terminal. Again, we have a neutral lead. It's not being used because it's a delta, so we'll just clamp it onto the insulation of one of the handles of the other test leads. So there you have your test connections. We're ready to go and see if we can do a test. So we're going to go in, we're going to select a new transformer. As we do that, it's going to ask for the configuration of the transformer. We know that this is a delta-delta transformer, so the far left side is going to be the primary. We'll select a delta, and then just on the other side of the colon is going to be your secondary side. We're going to once again select a delta, and then the numbers relate to a phase relationship between the primary and secondary, and because there is no phase shift, we're simply going to select 0 to indicate that. Notice the test voltage is set to auto, and I think we're all set up to go. So now we're just going to go press the go button, and then it's got a couple of questions for us. Do you want to test each phase at a time and stop in between, or would you just like to simply sequentially test all those? That's what we're going to do, is sequentially test them all. But we've pressed the emergency stop button. So we get that indication. We have to go twist that stop button to release it, and then press OK to clear that message on the test set. And once again, we're going to have to tell it to go do those tests. Now it's performing those tests. We had calculated some acceptable ratios and everything. The calculated nameplate ratio was 1.4574, if I recall correctly. And so it's listing what each phase has come up with for a ratio. Those look very close. Once we've gotten these test results, notice that we've gotten to a safe indication on our test set, meaning the test has been concluded. At this point, we can do some other things. If we wanted to, we can print the test results, and you'll see that it prints those out to the side. This is one manufacturer's equipment. You'll notice, if you can look at the indications there, we've preserved the test results as well as any information that we put in relating to this test. If you wanted to, you could have put in the primary and secondary voltages, and it would have calculated a % deviation. What's acceptable is 0.5%. We can also save these test results, and if you press save, it's going to come up and ask you for a transformer name. Just for practical purposes here, I'm just going to put in Protec, and then when I hit enter, it's going to ask me for additional information. What's the transformer serial number? I'm just not going to put that in at this time, but you'll notice at the top that the transformer is now labeled Protec. We can go into archive, and you'll see that it's the only test results in there. And if we select all, we could have just touched the one, or select all, and then we can recall that. Now you notice there's no test results in there because it's looking at it in terms of all the information leading up to the test. If we wanted to, we could go back and recall those test results. And now you're seeing those at this time. So this test is done. All of our test results seem to fall well within the 0.5%, and you have performed a transformer turns ratiometer test.